The motivation behind our project, the Autocar, was to gain a deeper understanding of automatic safety features that are available in common cars, as well as a very basic understanding of the mechanisms of self-driving cars. Our objective was to modify a simple RC car to be capable of avoiding obstacles in a simple course without any user input. The modifications we added are a servo motor that allowed a bigger range of steering and more accurate control of the car's path, 3 ultrasonic sensors that were able to detect obstacles at a customizable distance. We have had considerable success in our objective. Our car is able to detect an obstacle and either brake or turn depending on the desired setting. However, due to ultrasonic inaccuracy, it was difficult for us to consistently dodge obstacles in its path. We had to completely fabricate a steering system from the ground up. We used SolidWorks to create the servo arm and the axle and attached it to the servo motor. We initially tried to secure it using a rigid and cheap foam that we found online. It was very easy to shape to our needs. However, it started wearing very quickly, and we had to change that plan. Finally, we decided to bolt down the servo motor to the chassis using a number 8 bolt. We initially wanted to use an accurate laser sensor, but it was significantly more expensive. We also considered using an Arduino color sensor, but it was very short-ranged and needed a lot of power. The sensors we ended up using were ultrasonic sensors, and they were set up in 3 different directions. Our first attachment iteration was using a big breadboard attached to the chassis using rubber bands. The problem with this design is that it was very difficult to attach the forward ultrasonic sensor without really long wires. We ended up using a 9 by 5 inch wooden plank and then using Velcro straps to secure the small breadboards that allowed us to keep the flexibility of the breadboard without the limitations of its reach. For our code, we wanted to use a finite state machine, but we had trouble implementing it. We also realized that the ultrasonic sensor cannot share trigger pins, and each one needed its own pin. Otherwise, the system would be significantly slower. We performed a few experiments with our robot. Most notably are the first and third ones shown on the screen. Our first test was a throttle versus current. We wanted to see how much current was being drawn at the maximum throttle so that we can make an accurate choice for the power supply. Our third test was actually a throttle versus distance, and it helped us decide which speed setting to use a DC motor on. If we could change something about our project, it's how much time we spent on designing the new steering system. We've experienced a lot of steering system failures, and they put us behind on coding and testing, which was the real purpose of our project. We also should have considered using a laser sensor for forward obstacle detection. The accuracy would have been really helpful in creating a tighter control system.